Just want to spend some time looking at some different problems that have happened over the years. Remember, these are HSC questions, so obviously this is the end point where we get to. Don't panic too much. 2006 I always like, because it was quite a difficult one. They gave us a hint. Starts off, use the tan alpha minus beta formula to go and show this lovely expression, which does look horrible, but actually it's not too bad. So when I looked at it, they gave me a hint, use this fact, and so I'm looking at things like tan minus tan, and I'm looking at what I need to prove, and I see a tan, and a tan minus tan. So that says to me that logically, okay, I'm going to make alpha equal n plus 1 theta, and I'm going to make beta equal n theta. And then I'm just going to sub into the formula and see what happens. And okay, I end up with 1 plus tan, that's part of what I'm required to get. And I've got a tan n plus 1 theta minus n theta. Well, I can tidy that up, because obviously n plus 1 theta minus n theta just leaves me with theta. Yeah? So I now have tan theta. So it's getting a little bit closer. They've got a cot theta, however. That's right. Cot is the reciprocal of tan. So if I divide both sides by tan theta, but also multiply by the denominator, or is that going to fix it? Hang on, let's have a look. I've got rid of the denominator, so I've got the 1 plus tan, still got it times tan theta, but now if I divide both sides by the tan theta, I've now got that expression. But of course, what we were just saying, the reciprocal of tan theta is cot theta, and there's the actual expression that they were looking for. So that was an interesting start to this little question, and it did catch quite a few people out. Now, just the comments the examiners made that particular year. This was not very well done, with a lot of presenting circular arguments, so basically ending up with the same line that they started with. Okay. However, a number of candidates successfully rearranged the given fact and then easily saw the substitution of n plus 1 theta and n theta that was needed. Many spent considerable time on this part. It was only worth 1 mark. So don't waste too much time on that question. Okay. Of course, that part I was to help us with the induction that was coming later on. So here's part 2 of the question, and we have to prove that tan theta, tan 2 theta, plus tan 2 theta, tan 3 theta, and so on and so on and so on. And that's the tan part that we saw. So tan n theta, tan n plus 1 theta is equal to minus n plus 1 plus cot theta, tan n plus 1 theta. All right, well, the first step, let's prove it true for n equals 1. So the left-hand side, oh, actually I started with the right-hand side this time. So the right-hand side, if I sub in, I'm subbing in 1 for n, so I get negative 2 cot theta, tan 2 theta. On the left-hand side, we know it's tan theta, tan 2 theta. Well, at this stage, they don't look the same, so obviously I'm going to have to play around with it a bit. I'm rewriting the left-hand side to be 1 plus tan theta, tan 2 theta, minus 1. So in other words, I've added 1 and subtracted 1. Now, the reason I did that is I'm going back to, I guess, part 1, where I'm looking at this relationship they got us to prove, and I thought, well, how am I going to use it? Okay. Because if you have a look at what we proved, I can say 1 plus tan theta, tan 2 theta is cot theta outside of tan 2 theta minus tan theta. And that was what we just did in part 1. But of course, I've also got this minus 1 part, so we need to end up with minus 2. If I expand out, well, I've got the cot theta, tan 2 theta. Cot times tan, well, they're reciprocals, so they must multiply together to give 1. So I've got minus 1. Sure enough, we get minus 2. So I've got them being the same thing. So that was just proving true for n equals 1 in this question. So hence, yes, it is true for n equals 1. So I'm going to assume it's true for k. So basically, the result, we want to prove true for k plus 1. So So the next one. So it is a series type, this one. So I'll approach it the same way, in that I'll rewrite the whole series to be, and I'll just add in the second last term there, because then that gives me my assumption that we just made to sub in. So when I sub in that assumption, I now have minus k plus 1 plus cot theta tan k plus 1 theta plus tan k plus 1 theta tan k plus 2 theta, and we have to manipulate this one. But again, I notice there's that tan, and I go back to the formula that we proved in part I. So I remember the tan could become cot theta outside of tan k plus 2 theta minus tan k plus 1 theta, but also I'll now have a negative 1 there as well. So what can we do with that? I'm just looking at it and I notice cot theta tan k plus 1 theta, there's a positive 1. I'm also, if I expand this out, I'm going to end up with a negative 1 as well. So we're going to get some cancelling there. So let's expand that out. I've also got my negative 1, grouped it with my minus k plus 1, because remember what we're trying to prove, we needed a minus k plus 2. So I've got that bit. So beaut, I can leave that alone. It's the rest of it I now have to play with it. So we've got the cot theta tan k plus 1 theta and the minus cot theta tan k plus 1 theta. So they obviously going to cancel. So I've now got minus k plus 2, cot theta tan k plus 2 theta. What is it we're trying to prove? I haven't got it on this slide. That's it? Excellent. So hence it is true for k plus 1 if it's also true for k. And by induction we can then say all of them. So quite a tricky little induction there. What happened in the HSC that year? Most attempted this part. However, many only earned the mark for stating the inductive step. I guess what they're saying is they only basically got the 1 mark for using the idea of substituting in your assumption to go in that. I can't believe they gave a mark for simply saying, since it's true for n equals 1, that seems a bit of an easy mark. Could not, as I was saying, it was pretty hard just proving for n equals 1 in that one. Could not prove true for n equals 1 as they were not able to link in part 1. But remember, for questions written part I and part 2, especially in an induction question, you think, well, why on earth did they ask the question like that? They're giving you a hint. You're going to use this somewhere. Consequently, they were not able to go and prove that inductive step. Okay, let's have a look at another one. This sort of is a series one, but instead of adding the terms, we're multiplying the terms together for this one. So if we multiply this expression, we'll get 2 on n minus 1. So a little bit different. But remember, induction is an idea. Still do the same idea. The first case in this one is n equals 3. So we're going to prove the result true for 3. So left-hand side is 1 minus 2/3. I get a third. Right-hand side also turns out to be a third. So that works out okay. So our assumption, where k is some positive integer, I didn't bother specifying k was greater than or equal to 3 in this one, so I guess I probably didn't need to use that fact in my proof. But I suppose technically I should have made k greater than or equal to 3 as well. So we're going to assume that to be true. Proof for k plus 1. Again, I'll do it the same sort of way, but instead of adding, we're multiplying. So I'll put in the second last term. All of those terms multiplied together is our assumption, and we assume that to be 2 on k minus 1. So now all we really got is a little bit of algebra to do. Hopefully we can show this is the same as 2 on k plus 1. I reckon I probably would have made the brackets all one fraction. Yep. So there's my first step. Top of that fraction now becomes k minus 1, which will cancel with the k minus 1. And there it is. Drops out quite nicely. 2 on k plus 1. So looks different, and that often throws people, certainly in an HSC. hang on, this is different to something I've seen before. But actually, that proof wasn't too hard at all, if we just follow the basic idea of induction of what we do. So, hence the result is true, and so on, and so on. Notice in my final line there, I didn't say greater than or equal to 3. I just said greater than 2 by induction, which is, of course, the same as greater than or equal to 3 when I'm talking about integers. Any reasoning why I would have done that? Nah, because in PowerPoint, it's really hard to write greater than or equal to. So I just said greater than 2. Okay, what happened with that question? So, many candidates actually did this one quite well. Submitted excellent responses, including all the necessary components of the induction proof. Weaker responses. Yes, people out of habit go and do n equals 1 for the first case. So the poorer responses wouldn't have done n equals 3. They would have tried n equals 1 and gone, oh no, what's going on here? Had an incorrect assumption for k, or incorrect use of the assumption, because they probably out of habit again went plus instead of multiplied. Algebra, well, if your algebra skills aren't that great, it's probably going to make it a bit hard to do that one as well. As I've mentioned before, and as examiners are saying the same thing, that rote learning of the idea, sum to k plus t, in this one caused huge problems because it's not plus, it's multiply. So how's this formula going to help me in this question? Okay.